I'm John Fragalla. I'm with Cray. I'm a principal engineer focused on data storage. And until my slides come up, the focus of my talk is to really look at the new Lustre features and how to address running a shared storage with mixed users. A lot of the challenges that we have in shared storage today is the ability to have applications that run really good I/O, not be affected by applications that are running really bad I/O. A lot of the people that administer storage systems here, you've seen a lot of users complain day to day is one day my applications run really great, next day my application runs really poor. Why is that? And it's really because of these what we call noisy neighbor, really bad applications running on parallel file systems that are doing small file unaligned I/O that's also affecting applications that are really doing good I/O. So today I want to talk about some of the challenges that we see and new features in Lustre that enables transparent use of HDDs and flash in a single namespace so that users don't have to really choose where to run their applications. They just want to run into a configuration, run their applications, and ensure that they want consistent results day to day. And then we have some performance results of a simulated noisy neighbor problem that we ran on a parallel file system. So like we mentioned, bad applications, lots of small files, metadata thrashing, unaligned I/O that runs on parallel file systems. These could be running like database, MySQL type of workloads. You have these RTMs or seismic processing applications that really run really well on parallel file systems, but day to day competing users affect those applications. And it's hard to pinpoint and how to control those users not to affect those applications that really want to have really good performance and run for days. So with new features of Lustre parallel file system, there's new features called progressive file layouts, data on metadata, and then with clustered metadata, multiple metadata servers to handle additional inodes and metadata target, metadata operation performance. I'll talk a little bit about what each of these progressive file layout and data on metadata means, but I won't go into too much detail as we have limited time. But in a shared hybrid file system approach, you have multiple metadata servers. You have different tiers of storage possibly. You might have a flash tier. You might have a really high-performing disk tier. And then you might have a really slow-performing disk tier. And you want to really pinpoint where your applications should run to accelerate transparently applications that are designed for different types of media devices. So you might want to run small I/O and isolate that to small files. You want to run your streaming I/O, which really has large sequential I/O, maybe just needs to run to disk. And then over time, you want to archive that data, and you want to do it all transparent to you in a single namespace. And then today, and historically, you would actually have to migrate data, move data lots around, and you would have to have different namespaces for different types of media devices, and then choose which applications run where. And with new features in Lustre, you could actually run this all in a single namespace and create different layouts to pinpoint where data should sit on any given size of a file. So with progressive file layouts in Lustre, it allows you to create a layout where you could actually start writing a file on flash, and as that file grows, it spills over to disk. As that file grows even more, it could stripe that data over multiple OSTs. And that flash piece of it could be metadata, or it could be a specific flash pool of OSTs on Lustre. And as you grow that file, it transparently holds extents of those files in different storage medias. But from an application perspective, it doesn't even know where it's sitting. All it knows is it's just running on a Lustre parallel file system. And then this is where storage pools, which has been a technology used in Lustre for a very long time, not really used in production a whole lot, but with storage pools, you could actually create a layout and target and isolate how you want to write files to different storage media. So you create a pool of flash, a pool of disk, and even a pool of high-performing disk. And then create that layout with different pools, and then say, I want to start writing my file up to, let's say, a megabyte. I want to write to flash. As the file grows, I want to write on a stripe count of 1, meaning you want to write to one OST randomly to a disk. And as that file continues to grow, I want to automatically stripe my file across multiple OSTs. transparently for me as a file grows. From a user perspective, an application perspective, when you run ls, there are no changes to how you actually view that file system. But when you run low-level commands that are Lustre specific, it actually tell you what extents of what file is partly stored in what devices. And what data metadata allows us to do is actually reduce the latency of small file overhead in Lustre. With Lustre, historically, is really good with streaming I/O. As many of you know who run Lustre, it's really poor on small random or small I/O accesses because you're really just threading metadata thrashing, as well as because most of the OSTs are RAID 6, you have the read, modify, write overhead that really reduces the performance of small I/O. The notion of data metadata is if the file is small, why do I want to write to an OST and increase the protocol overhead of Lustre of communicating between client metadata back to client to OST? If the file is small enough, let that file stay with the inode and write that file starting on metadata. And then you reduce the latency of accessing small files because you have less protocol overhead to negotiate where to write that file on Lustre. And that's the notion of improving small file performance on Lustre by storing that file on metadata. And it's an extension of the progressive file layout. You create a layout starting with the MDT, and then usually, on average, you have the default size of 1 megabyte. You could go as low as 64K, and with some comp parameters, you could increase that. I wouldn't recommend going beyond 1 megabyte because you want to also secure that you have enough inode space to store your inode solution for how many files you have in a file system. So you want to balance your metadata sizing. And you could actually, with DNE2, you could actually have multiple metadata targets contribute to data on metadata. So if you create a Stripe directory of 4 metadata targets, for example, you have the ability then to store randomly depending on load of the file system, where those initial 1 megabyte extents are stored on any random of those 4 metadata targets. And as you grow, then you start writing to the OSTs. The only limitation of data on metadata is you can't stripe across metadata targets. There's always a stripe count of 1. So if you want to write and have multiple stripe counts on a flash-based target, you want to maybe not do data on metadata, but maybe start writing to a flash-based OST, and that has you a little bit more flexibility of stripe count of multiple targets, as well as increasing your stripe size beyond 1 megabyte. And you could actually grow as large a layout beyond 1 megabyte. But really, data on metadata is really targeted for the small files in the kilobyte range, hundreds of kilobyte ranges, up to 1 megabyte. And then with DNE2, you could actually do stripe directories now where that you could have multiple metadata targets, clustered metadata is what we typically call it in Lustre, and actually have it transparently run on your parallel file system. Now you could have the ability to say, I have 4 metadata targets configured on a file system, and it will automatically load balance your inodes across all those metadata targets. So that allows you to do a couple of things. 1, improve your single shared directory performance. 2, increase the number of inodes supported in your parallel file system. And 3, with more metadata targets, you have more performance, with more file crates, more stats, more reads, more deletes. So the benchmark that we ran to simulate a noisy neighbor problem was we used flash-based MDTs, and we had 4 MDTs to test with. We also had 2 flash-based OSTs in an IOPS configuration. So what that means, we configured those flash-based OSTs in a RAID 10 configuration to avoid the read, modify, write. And then we had 4 OSTs of hard drives in a parity declustered configuration, which we use grid RAID from Cray. We had up to 64 clients, FDR connections to an EDR fabric. We had Spectre Meltdown enabled on the clients. We had Spectre Meltdown disabled on the server. And we're running Lustre 2.11 on the client and server. So the first thing we wanted to do was just prove to ourselves that progressive file layout doesn't have impact on performance. So what that means is that I created a layout where I wrote with different files layouts, where we had a layout of 64 kilobyte file size sits on metadata, and the rest spills over to disk. we had a layout of the 256 kilobyte file size sits on metadata. The rest spills over to disk, 1 meg and 4 meg. And then we had no DOM, which means that we just wrote directly to the disk-based OSTs as a baseline. So this is a large sequential IOR job that really maximized our storage configuration of the benchmark that we had set up. So we had roughly around 25 gigabytes per second of throughput with no layout, just standard stripe count of 1, basically our hero number benchmark. And then with different layouts of that first 64 kilobyte of each of our ranks of files being written to this layout is written to the metadata, or 256 and so on and so forth. Basically, what we're saying here is a large sequential I/O performance, regardless if we use a layout of flash-based MDTs of different file sizes, we have really no performance difference on our sequential I/O performance. So test 1 proved that our PFL doesn't hurt performance for sequential performance, which is what we wanted to test with. Now we wanted to introduce a noisy neighbor or a competing workload. So what we're going to benchmark and show you is the results of the sequential performance. We're not measuring the performance of the noisy neighbor, but we're going to show you the effects of the impact of performance it will have on the sequential performance when we introduce the competing workload. So we have this nice streaming workload, really designed for parallel file systems, all hitting Lustre OSTs created of disk drives. Then we had a small file workload of 1 meg or 4 meg files, really competing against that same OST target or same group of parallel file systems running on disk. We'll show you the impact it has with no layout, meaning that you just run today, everything's competing for resources from all your clients, mixed workload, and you'll see the impact of performance it will have. Then what we want to do is take that same streaming performance and then create a layout where it gets absorbed into Flash. And it could be a Flash-based OST target or a Flash-based MDT target. And we'll show you the effects of a different layout, and even with the wrong layout, your performance can suffer even worse if you're not sizing the I/O pattern to be absorbed into Flash. So let's look at some of the baseline performance. So right here, you're looking at a 1 meg competing workload file, and here we're looking at a 4 meg competing workload file. The reason why we went so big on a competing workload, because our benchmark setup was really limited. If we had 1,000 of clients and we had a large pool of storage resources, our competing workload would have been around 32K. But 32K in our small benchmark setup did not have any impact to sequential performance because of just the benchmark setup we had. So we had to go bigger on the competing workload, which is why it's 1 meg. So what we have here is a baseline of our sequential performance, no competing workload. So again, 25 gigabytes per second, great I/O. Now, in normal operation, we have multiple users hitting that file system. So this is where user A goes, hey, yesterday I ran really good performance, 25 gigs a second. Today, I'm running slower. I'm running about 20 gigs a second because now there's a competing workload running 1 meg small file access, and our sequential performance is suffered by about 5 to 6 gigabytes per second of read and writes. So if we know that our competing workload has an I/O size of 1 megabyte, I want to isolate and absorb that into our Flash-based target. And this could be a Flash-based MDT or Flash-based OST. I create a layout that the first megabyte of the sequential performance and the competing workload performance are always written to Flash. So they're all writing to the same layout. Because now the 1 megabyte is not hitting disk, it stays on Flash, our sequential performance comes back up to close to non-interfered performance. Now we do the same thing here, a 4 meg file. So we created the same layout. We have no layout for a baseline. Then we have an interfered benchmark of 4 megabyte, no layout. We have a 1 meg layout and then a 4 meg layout to Flash. So basically our baseline is exactly the same as this. Really good performance, 25 gigs a second, great. We introduced this competing workload of 4 megabyte against the sequential performance, and you can see a bigger impact of performance on writes and reads. This is no layout. Everything is hitting disk. Now we create a layout that says the first megabyte of every file is stored on flash. The remaining gets bleed over to disk. So that means even the competing workload, the remaining 3 megabyte of those files are still competing on disk. And this tells me that even the wrong layout, even though you have now flash being transparently used, your performance goes down because the layout wasn't designed to absorb the competing workload in its entirety. As we increase the layout to 4 megabyte to match the file size of 4 megabyte, everything of that competing workload is now sits on flash, and also the sequential performance, that the sequential I/O is also says 4 megabytes sitting on flash. And then as it increases the file size, it bleeds over to disk, the performance comes back up. So we have to understand the I/O profile we're targeting to isolate the noisy neighbor or the competing workload transparently so that you don't have this negative impact on return with a wrong layout. But you could actually create a layout that we know that will absorb those competing workloads so you have much better predictable performance day to day than you have today when you don't have a mixed environment. And this allows you to transparently also use different media technologies without having to do point targets of running applications on different media devices. Now, if you want to run that way, you could actually run that I want to create a storage pool flash and a storage pool disk. I don't want to do a layout, but I actually know that this application will run always good in flash. You could actually target that application to run only in a pool of storage on flash. And you could actually run that way too. And you could actually run your files where that you could actually create multiple layouts and multiple configurations in your file systems where you know that you always have a good application that runs streaming I/O performance on disk. I don't want to run a layout. I just want to run on disk. Then you have other workloads that are mixed, and you know those competing workloads will be isolated. You could actually create a different profile layout for those other applications and run that layout that way. So it's really flexible how you want to run this with different Lustre features to enable the isolation of mixed workloads and interfered noisy neighbor problem. So in summary, with the new features of progressive file layout, data metadata, multiple metadata targets, you actually have the ability to transparently leverage flash and disk and isolate applications to try to improve your predictability and performance day to day. Thank you.
Hey, John, you mentioned the streaming workload quite a few times. How do you define streaming? Because I will ask you, this is not a stupid question, okay? We are not talking, in HPC, we are not talking about the Netflix type consumer streaming. The stream can be from single source, which is trivial, but multiple source, just think of two, suddenly becomes very complicated. How do you define stream? You don't have the guarantee of a sequential receiving order anymore. So could you describe how you define your streaming?
The way
workload?
that we described it in this synthetic benchmark, right, just to simulate the noisy neighbor is large block, large streaming I/O, aligned I/O with multiple ranks, really aligned with the Lustre stripe count and stripe sizes.
Multiple sources?
Multiple clients, multiple ranks per client.
Now how do you define streaming? Because the receiving order is...
Aligned I/O. It's basically aligned I/O. Again, this is not to mimic general application use. This is to generically demonstrate isolating the noisy neighbor problem in a synthetic way. Now, yes, thank you.